Hi, welcome back to Tech Savara. Previously I wanted to show you about Jupyter Notebooks, RocketPy, how we could possibly do that. So we're going to get straight back into that. We're going to continue it. I want to see if I can actually get it to work. The previous episode was really kind of stuck in the weeds of just getting Jupyter Notebooks to open. I would have thought that it would be easy, just as easy to install it, to set it up, and then we can just run a rocket simulation. So RocketPy, previously I mentioned, it is for simulating rocket flight. It's got an engine model, it's got an environment model, a rocket model. It'd be interesting to see what those parameters are, explore it a little bit, but to start, I just want to use their example to actually generate a rocket flight experience, would like to simulate it. I think it's huge. Everybody's into rocketry, space exploration these days, so why not? Let's see where we can take this flight. All right, guys, let's jump straight into RocketPy. Let's not waste any time. Let's explore the code and jump right back to where we were before. So back to where we were before, straight into it. We had Jupyter Notebook, which we just got working because we were running it out of PyCharm. And we have it still kind of running here on a local server. And we have it here, and we have the example. So the last thing we did was just to get that working, just to have Jupyter Notebooks running. We really didn't do anything with RocketPy, so to speak. So it was really more about how to get started with Jupyter Notebooks. But right now, let's see, we have some flight examples and development. Let's see what we've got here. We do have some flight examples that we want to do. Interesting. But we don't know. We want to just use a code reference. User guide. First simulation. Okay, this is where we want to go. We will have an environment. Okay, so we have the initial import. We've done that. Next thing we want to do is we want to specify the date time. And so we've got import date time. And then we do, so I guess tomorrow was date time dot date dot today plus date time, well, time dot time delta. So plus date time day one. Okay, so yeah, daytime is today, and we add the daytime instance of 1 day to get tomorrow. So that's time delta. First time I've used that, I think. Never really explored much time stuff in Python. Anyway, so now we just do the end dot set date. So we have our, wait, where's our environment? Oh, we need to actually, we need to n equals, actually, this is probably environment. Let's just copy and paste this. Look, I'm not a big fan of copying and pasting, but if I'm typing in numbers, I might as well just copy and paste them. I do like to type out code just to get in the habit of typing the things, to learn them, like physically learn certain things. We have our env, we want to set the date. Okay, that makes sense. And we got tomorrow. Oh, it's not just date time, we have to specify the time, day, tomorrow dot year, tomorrow dot month, and tomorrow dot day. Actually, I missed out on my task today to do this type racer. It's a website that I use to type race, so I can type faster. And we've got that. That's easy. Oh, it's tuple. So we've got to set that up as a tuple. Why that's a tuple, I don't know. But anyway, okay. We want to just move this, and I'll run this block here. Let's run it all. Okay, we run that, and then we have this import date time, and we've set the env. We have the env here. We'll run that. Yep, all works. And model, we got an env. This is what we tried to do last time. Here we go. I got it here. This is the actual code I tried to run that, it could probably run, but they recommend doing Jupyter Notebooks, maybe because they have some graphical representation that they want to show. So type equals forecast. Yep. We have file equals GFS. All right. Oh, set atmospheric model. Didn't like that. Forecast. Environment object has no attribute. Atmos set. Okay, what did I do wrong here? That looks exactly the same. Oh, God. Oh, no, it works now. Environment.py itself, windy atmosphere file, raise value error, unknown model type, GFS forecast. Okay, forecast. So, wonder what I actually, how I misspelt atmospheric model. And what was it before? Atomspheric. Ah, see? It's so easy to make these kind of mistakes. But this is how you learn. This is how you learn what to do and what not to do. So, let's fix this forecast, and that should work now. Cool. Server error retrieving URL is not an available data set. Wow. Okay. So something's gone terribly wrong. I can't access that data. And which means that this will probably not work either. Oh no, it worked. It just there was a server error for something. I couldn't get something. Oh, look at this. We have graphs. So we have wind direction at the specific height. We have the density of the speed of sound. So we have that. It's a linear model of height against the density of speed of sound okay, the speed of sound and the density of what? Density. Oxygen density, atmospheric density, surface air density, kilograms. Oh, maybe that's the pressure. Surface atmospheric. Wow, this is really cool. Look at this. Look at all this information we have. We have gravity details, acceleration of gravity at surface level, and acceleration of gravity at 80 kilometers. So it's different, right? So gravity changes as you move further away. So it's actually less effective. So that would mean is the closer you get to Earth, the more intense the force of gravity is. If you get to the center of the Earth. So that's why you really want to take off at higher latitudes, right? At surface level, possibly. You know, if you could take off from, say, Mount Everest. So we had the elevation at 1,400 meters. What about if we do 5,000 meters? Let's run that. Let's run this. Run, run. Oh, let's run this. What? What happened? We had some oh, here we go. 97911. So can I change that to 8,000 meters? That'd be Mount Everest, thereabout. Okay. Right. Try rerun. Do you want to restart the kernel? All variables will be lost. No, I'm scared that it's going to delete everything. This is the problem. This is restart the kernel and run all cells. Okay, restart, run. This. Come on. Okay. Yep, yep. What happened? Oh, I think it just took some time to calculate. Um, elevation at surface level. So we're not launch site longitude 32 minus 106. This should be surface elevation. So this didn't even set that surface elevation. Wait, this is weird. So I set the surface site elevation and it's not giving me what I want. It's still giving me a. What about if we delete that and we just restart? Yep, restart. Okay, run this, run this, run this, run this, run this. Okay, cool. And then we run env.info. And then Let's see what happens. We still get this surface elevation. What about if we do elevation 0? Okay, stop. Let's restart everything. And then that's okay. Let's run all the cells. It's running. Yep. And now it's still running. Just generate the info. And it's still giving us 1471. You know what? It could be that the elevation is based on, let's have 102, right? So if we restart it, we could be getting the elevation at that geographic location. Maybe that's what it's doing. Restart and run. Possibly. I could be wrong. But we've changed it to some other place. And what is it giving? It's 102. Okay. Surface elevation. So what is the GPS location of Mount Everest? Really interesting. So what do we in this 7? The gravity is greater, right? So Mount Everest height location. Actually, Google Maps. What is the uh, at? Here it is. Mount Everest Google Earth at 27. I just want to get the values. Like I just want to get the values. All right. Okay, great. Explore Google Earth. What is this? Where are we? Where is this? No, I want the values. Cursor. What? Why don't you just give me the actual values? This is a, let's go to Google instead of DuckDuckGo. Where is it? Here we go. 2786. Go here. 27. 27 and 86. So let's try that again. Elevation doesn't seem to make a difference. Okay, running again. And what do we get? Eh, 7739. So, I mean, look, there's less force going down. So it'd be interesting to see how much you save, but probably not much. But then there's also the height difference, right? And there's also, I mean, you could do something. Who knows? I wonder what difference it would make. Um, there is a motor. Let's write this out. And the reason I want to write this out because I want to talk to 7M1670, right? And we have a solid motor here, and the solid motor is a thrust source. Okay, we have this. We have a thrust source. I'm not going to copy that out because thrust source. What is that? What is the thrust source? Does that describe the actual type, the dry mass? Dry inertia, dry mass? Dry mass. I don't know anything about this stuff, but I'm learning as I go. Okay, dry mass equals 1.815. So that's the mass of when it's dry. Yeah, inertia. Kind of like stabbing in the dark. Like I feel like I'd want to do a wiki search for every single item here. 0.125, 0.002 dry inertia. Okay, so that's the inertial values, probably XYZ maybe. Nozzle maybe, I don't know. What is dry inertia here? Does it tell us? Doesn't tell us anything. So let's try nozzle radius. Okay, radius equals 33 over 1000. We have grain number. Okay, what is the grain number? There, I don't know anything about any of these values so far. So there's absolutely nothing. Grain density. So there's plenty to learn here. Grain density. as the 1815. Okay, so we have okay, because I don't know anything, grain center of dry mass position. Okay, maybe that's the dry fuel. Maybe dry fuel could be dry fuel, wet fuel. It's a solid motor with dry mass. All right, let's just copy and paste this down here. I don't know anything about any of the values. Nozzle combustion chamber, coordinate system orientation. All right, so there's that. Next, what we have, we can run this. See what happens. It doesn't like it. So, we don't assign it to anything. Maybe row 7m 75m1670 equals. Does that do anything? It doesn't seem to do anything, right? So let's try to get no such file or directory. We don't have. Oh, damn. Okay, data. Where do I get that? Rocket can simulate solid hybrid. Okay, well, this is a solid motor, right? So it's solid fuel. But where do we get the file? We have Cicerone thrust source. Okay. Finding a rocket kind of makes things difficult. Where do I would have to go and check out the notebook file. Is that this in GitHub? So where would be okay, it's loading. Notebooks, environment, Cesare examples, data. Okay, Cesar data. Callisto. Maybe if we go data motors. Okay. Copy link. So this should if yeah, let's see. Does it accept the URL? Let's try that again. It would be great if it did. Yeah, no, it doesn't accept URLs. Okay, so the other one is we'll just to see if we can download this. Download linked file. Yay! And we will move this file into our test folder. Yes. Yes, refactor there. Okay. The what? HTML? What is it doing? Okay. It's not what. And just rename that. Let's get rid of the HTML extension. Should definitely be easier. So because we're running in here, we can just go. We should be able to just go. Sorry, .eng. It's because it's in our folder. I would expect this to work. Excellent. That's how you do it. We're almost there. So we got the files here. Let's see, defining a rocket. Okay. So this is the Callisto rocket. Same thing. We're going to define a rocket. We're going to get these files from data Callisto. Like we have here, data Callisto. And we'll just get, can we get all the files? Can we just get all the files? Copy path. Download linked file. So link is a URL, right? CSV. Okay, code. Let's just copy and paste the code. And we want, but we don't want to copy the path. New file. New file. New file. What's it called? NACA 0012 CSV. Let's move it here. NACA. New file. And NACA 0012-radians.csv. I'll just drag that in there. Yep, cool. Save. No, dismiss. Ignore extension. Go away. Upsell. So what do we have here? We need Between all the things, we didn't even need that. We needed the power off and power on drag curves. All right, so code. Okay, let's copy that. Power on drag curve. Same thing. New file. Power on drag curve.csv. Interesting. What this actually expresses, right? So, and then we got, yeah, let's do a new one. File power off drag curve.csv. All right, power off drag curve, power. This is the power off drag curve. So that's that one. And then power on drag curve is this one with code. Copy and paste. Okay, beautiful. We have that. We have this. We don't need this at all. We just use the files directly. Okay, we don't need the other CSV files. So this should work. So we've got the two files, the drag data sets, and voila. Beautiful. Okay, we're getting somewhere. We're getting somewhere. Getting on a rocket. On a rocket. Okay, we add the motor. So we want to add the motor to Callisto rocket. Okay, yep. Runs. That works. Now we also add rail guides to the rocket. These are not necessary for a simulation, but they are useful for a more realistic out of rail velocity and stability calculation. Okay, very interesting. I mean, I really hope that both SpaceX and Blue Origin and any other rocket company is really contributing to this, because I think it's really, I mean, people talk about open source, right? This code should be really, really useful for a lot of people. Simulating rockets will reduce cost a lot. So yeah, I mean, we have our neck. Oh, finally, we have our Callisto add nose, add trapezoidal fins. We have this in model, the airfoil. Okay. We have the tail. Okay, let's run that. Cool, we've got it. We're getting there, getting there. Next up, we have our parachute. We don't. Okay, let's just drop these in. Oh, we have our parachute and yeah, we have two parachutes. It's probably for drop. Let's see if that works. Okay. And then we've got static margin. Well, we can see if the rocket is stable by plotting the static margin in, what is that, in C? Radians? Great. What is that? CS. I don't know what that measurement is. And you always check the static margin of your rocket. If it is negative, your rocket is unstable and the simulation will most likely fail. Interesting. So much to learn here. What about if, let's change something. Let's change the lag, ejection at apogee. We don't need the drag. We want the root code Callisto add trapezoidal fins. We want the position to be 1.1. Okay, we'll run that again, and then we'll run this again. Ooh, 3.6. Nice. I have no idea what this means, but we're getting some. It'd be great to actually see. Oh, right. Okay. This is awesome. How cool is this? I get to actually see the rocket after I've rendered it. Wow. The fins are bigger here. I've got two of them. It looks different to this one here. What about if I know why that is? Let's change that back. Add parachute, add fins. At the position 1. I think I might have done something. It's not meant to be done. Let's try run that again. Run that. Run this. Plot the static margin. We're back on. Oh, 3, 4. Let's see. Can we draw the rocket? Oh, it's getting very confused now. Let's move this. Let's 0.0104. Okay, let's we'll put 104. It's negative 104. So the further negative obviously would be behind the rocket, behind something. Callisto trapezoidal fins. What about if we did? Well, I don't know what that position is relative to, right? So I was just kind of like, yeah, Let's rerun it. Restart and run everything. Cool. While it's doing that, we will jump back. We've got a static margin. If it is unreasonably high, your rocket is super stable and the simulation will most likely fail. Also, interesting. Okay, we have the rocket that matches this actual diagram. So we have center grains, center of mass grains, nozzle, and center of mass, static center of pressure. Oh, this is cool. Okay. To simulate a flight, we need to create a flight object. This object will run the simulation, store the results. Okay. So we'll run the simulation. Let's do that. Next, we want to RocketPy has two submodules to access the results simulation, prints and plots. Also, each class has its own method to quickly access all information. For example, test flight all info for visualizing all the plots and test flight info for a summary. So let's do the summary. You may want all the methods that are used in this section can be accessed at once by running flight info. Okay, initial conditions. So we'll do that. So we can do it. Okay, we have our initial conditions, surface wind conditions. Interesting. We have surface wind conditions. And then we have full test prints, launch rail conditions. Launch rail. Okay, they're the same. And now we have out of rail conditions. So I'm not sure. I think rail might mean the whole container for it. Maybe, I don't know. Let's see. Let's burnout conditions. Burnout conditions. Let's run it. Okay. Okay. All the methods used in the section can be accessed at once. Okay, let's just do this. All info. Let's just run all info like this. Okay, that gave us all of it. But what about if using the test flight plots module, we can access multiple results of the simulation. For example, we can full trajectory. This is exciting. So this bit is where I'm going to wrap up. I'm going to do the full trajectory, and then I might actually dive in some. Oh, there we go. We get to altitude above ground level in meters. We get to 3,500 meters. Okay, interesting. Wow, so the wind pushes it all the way up over here. Well, guys, we did a rocket simulation. A lot of it was copy and paste, and it was really kind of just exploring the different options that we have here. But it's amazing that you can actually generate all of this rocket data set, all these data sets, and then just plot them. So the idea would be really from here is you dive into each step, learn about each module, about your rocket, your motor, your environmental conditions, and then experiment with different sets of values, and then try different simulations. I mean, the one thing that I want to know is what is a grain, what is all this information, right? So it's worth at this point to kind of dig into what specifically you want to experiment with, right? And understand what each particular thing does, right? You've got rail departure state. I don't know anything about this stuff. But it's a great way to introduce myself to a topic and open the doors to all these different ideas and paths and things that I can explore to understand more. And if I ever really want to dive into rocketry, I'll do that. I mean, I I am I guess next week, right? I want to dive into something else. I am really interested in rocketry. I'm not so interested in the AI kind of stuff in Mojo, to be honest. Like it didn't really pique my interest. So I'm not I'm kind of like bad taste in my mouth after all the AI co-pilot and stealing data and all this kind of stuff. So yeah, I'm not really interested in AI, generative AI. It feels like it's just in bad taste. It's all in bad taste, right? For some reason, there's just something that I think is that I can see some of the value in what it does, but I don't think it's going to sharpen our ability to solve problems. These are the problem of software is not a code problem, right? So coding is the easy part. And I can't even trust the Copilot stuff to actually do the code. So AI just in general is like, if I want to code something, it's pretty easy. That's not the hard part. The hard part is actually finding ways to solve problems and understanding the language and the semantics, so you can actually approach a problem in the space that's in, like rocketry, for instance. There's all these terms that I need to learn. So the next step, I think next week, I actually want to get into more firmware related stuff. Look at Canvas, and maybe even Canvas simulation. Possibly start looking at embedded firmware, embedded software, working with Arduino. So we'll see. We'll see what happens by next week. But there'll be another video more related to firmware, low-level software development, maybe in C. So we'll talk about that next week. Thanks for tuning in, and good to see you. I will see you at the next video. Bye.